Hello, everyone. So welcome to the fourth lecture in topic 5.4. Today, we will be talking about the fields of a solenoid, and also we'll also be talking about the forces acting on a charge moving in the magnetic field. So that will be our main tasks today. So let's start with the lesson. Before we move on to the field of a solenoid, let us recall a little bit about the field due to a circular wire. As you might remember last time that I said, if you want to find the field directions of a circular wire, magnetic field directions for circular wire, you just draw S or N on the inside of the wire. So if I make an S here like this, I see that my arrow points in the correct directions for S. So which means for that particular wire, circular wire, I'm looking at the south face of the magnetic field. Similarly, if I make an N here like this, I can see that I'm looking at and it also follows the directions of the current. So I can say that I'm looking at the north face of the magnetic field. Now, the red arrow here is the directions of the current. Okay, so in this case, the current is moving in the anti-clockwise directions, and in this case, the current is moving in the clockwise directions. So, yes. Now, this is how we found out the directions of the magnetic field directions of the circular wire. Now, using the same concept, we will try to understand the magnetic field directions of the solenoid. So solenoid is nothing but a many wounds of the wire. So if you wound a wire in a circular shape, then you have a solenoid. Now, in this case, as you can see that you have a wire that's sort of circular, right? Almost circular, but not circular. So we can use the concept of a magnetic field of a circular wire in order to determine how the field of a solenoid looks like. Now, if I say the current is flowing in this direction here, okay, so the current is flowing in this direction, and from the other end, it's coming out. Now, you know that the current is flowing in the clockwise directions, if you look at it, right? Because this goes back, and then this comes front here. So if you have a circular wire, okay, if you have a circular wire, and if the directions of the current is clockwise, then, like I already said, you just draw a S figure here to align with the directions of the current. So you know that this end, the face that you're looking at behaves like a south. So that means for this particular circular wire here, this behaves as a south. But as you can see, the circle is repetitive, right? Because you go to the next loop, here. This is still a circle here, and the current is still flowing clockwise. So this still behaves as a south. Okay, so likewise, so all the circles that are formed here always tells us that the face that we're looking at is the south. So if the current is flowing in a clockwise direction, the left side of the solenoid will behave like as if it's a south pole. And likewise, the other end of the solenoid here will tend to behave like a north pole here. So this will tend to behave like a north pole because the other end of the other side of the solenoid would be a north pole. So having understood this much, now it's very easy to draw the field diagram of a solenoid once we have determined which side is the north and which side is the south pole. Now let us draw the field diagram of a solenoid. So I've redrawn a solenoid that we just analyzed. Okay. So in this case, what I said was the left side behaved like a south pole. Okay, this is still a clockwise current flow in this particular solenoid here that I've drawn. So this is like a south pole. This end of the solenoid behaves like a south pole, and this end of a solenoid behaves like a north pole. So if you want to draw a field diagram, you know that the field is circular, right? In any magnet, the field is circular. So in this case, the magnetic field moves from the north pole to the south pole. Okay, so this is something that you have to remember here. And there'll be a field lines inside like this as well. And let me also draw the field lines below here, one of the field lines here. And this is something like that. Okay. Now that is something that we can all understand based on the field diagrams, right? That the field lines should be curved like this. Okay. Because once we have identified which side is the north and which side is the south pole, we can literally draw a figure that looks like this. Okay, so this is how we draw a field lines of a solenoid along with the directions of the field lines. Now let us try to understand which one in this particular field diagram is north and which one is the south pole. Okay, it's pretty straightforward if you look at the direction that this should be a north and this should be a south, right? Because the field lines always move from north to south. But what I'm trying to do here is I'm trying to verify here that this indeed will be a south pole. Sorry, it will be a north pole if the direction of the current is this side like that. Now, like I said in the discussion just before, if you have a circular wire, like so, like if you have a circular wire like so, then if the current is flowing in the, now look at the direction of the current here. So this is anti-clockwise, right? So anti-clockwise is something like this. So the current flow is anti-clockwise, and if the current flow is anti-clockwise, then you know that the type of arrow that you'll have to draw is something like this. Okay, so you write N, and N here does give you the correct directions of the current here. So this goes that side and this goes this side. So the phase that you're looking at will be the north pole here. So it is indeed correct that the field lines here correctly represents the north pole and the south pole. Okay. Now you might be wondering, so why not just put south here and then check if it's correct or not? If I do south like this here, then I'll have to draw an arrow like this. So if I draw an arrow in this direction, then it's not in the direction that we want, right? Because the current is going in the anti-clockwise directions and this is pointing in the clockwise direction. So that's how we figure out which side of the solenoid is a north pole or a south pole. Next, we'll move on to the force on a charge moving in a B field. So if we consider a bar magnet, two-bar magnet, whereby you keep a north pole and a south pole in alignment, then if we want to draw a field diagram here for this one, So like I said, the field always moves from north to south, right? So if I want to draw magnetic field lines, I would draw something like this. Okay, so I would draw something like this. So that's a field line. That's a magnetic field line. Now, the blue dot here with an arrow is basically a charge. So let me just redraw that. So let me just redraw that to let you know what I'm doing. So if we consider a charge, okay, a charged particle somewhere here, it's zooming through the magnetic field. It's zooming through the magnetic field. So there are some observations that we can make when a charge moves through the magnetic field. Okay. Now, because we are looking at the force, we will look at what factors determine how much force acts on a charge moving in the field. Now, there are 4 observations that we can make. Firstly, how fast the charge is moving. If the charge is moving fast, then we observe that the force is more. So the first observation is basically that the force on a charge is directly dependent on the velocity of the charged particle. That's the first observation. So for example, if you have a charge moving at 20 meters per second and a charge, the same charge, identical conditions, and the charge moving at maybe 30 meters per second, then you will observe that the charge moving with 30 meters per second experiences more force than the charge moving with 20 meters per second. Okay, so that's the first observations that we can make when we let the particle go through the charged particle go through the magnetic field. Now, the second observation could also be made, and that is the force is also proportional to the charge of the particle. Now, if you keep all the other conditions to be the same velocity, the same magnetic field strength, and so on, you will find that force directly depends on the charge. So if the charge is bigger, then the force experienced by the charge is also a lot bigger. Okay, so that's the second observations that we see when we conduct this experiment. And the other factors that affecting the force here is also the magnetic field. So the force is also proportional to the magnetic field. The stronger the magnet you choose, the stronger the force that the charge feels. Okay, so that's another observations that we can make in this experiment. And the last one is basically the angular dependence. Like if you send a charged particle, at certain angle with the magnetic field, then force is also directly proportional to the sine of the theta. Okay, so it's proportional to sine of the theta, which is to say that if the angle between the velocity and the magnetic field is 0. So okay, let me just say what is theta here. So theta is the angle between V and B. So the velocity, the directions of the velocity and the directions of the magnetic field, if they are 0, then the force is 0. And if it's 90 degree, it's a maximum, right? Because sine of 90 has the maximum value in a sine function. So these are the 4 observations that we can make if a charge is moving across the magnetic field. Now, to summarize all of this, we have a very simple formula that can take into account all the different factors affecting the forces on the charged particle. And the formula for that is basically force acting on a charge equals to BQV sine theta. So this is the formula for the force that's acting on the charged particle moving through a field. Now, this is a fundamental definition of the force acting on a charge. Okay, so there is no question like, why is this formula true, and so on, because this is an observations that we have made, and this turns out to be true. Okay, so let us try to do some questions that's related to this one. Okay, so let's do that as our next task. Before we move on to the question, let us try to understand the angles in a little bit more detail, because most of the students get confused with what is the angle that we're talking about here. So if you assume that the velocity is moving right in between the two magnets, then this is the angle that we are talking about here. So in this case, in this particular situation, we know that the angle is 90 degrees. So if a charged particle is moving in perpendicular to the directions of the magnetic field, then the angle should be 90 degrees. But if the particle is moving in such a way that it is moving along the field lines, so instead of this, if we have a particle that's moving along the field, so maybe the particle is moving from this point to that point here, like that, it's moving along, then the angle between the magnetic field and the velocity should be 0. So in this case, the angle is 0. Okay, so it is precisely in this particular condition that the force on this charge will be 0. If it is moving along the direction of the field, the force is 0. Now, it does not matter whether it's moving along with the field or in opposite direction to the field. The answer will still be the same. It'll still be 0. The force is most effective when the angle is 90 degrees, and that's the angle that I have already shown. So it's like when it's moving right at the 90 degree with the magnetic field. So if it's moving at the 90 degree, then the force experience is the maximum. Now, it could be anywhere. It could be like the particle is moving up. So it could be the particle is moving up like that. The angle is still 90 degrees, right? It could be it's coming backward like that. It's still 90 degrees. It could be it's moving sideways. It's still 90 degrees here. Okay, it's still 90 degrees, but it's difficult to show here, but it's still be 90 degrees. There will be a plane where it has a freedom of motion. So in that whole plane, the forces acting on the charge will be the maximum. Let's talk about the direction of the force on a charge when it moves across the magnetic field. And this one, we will do it by a rule. Yes, another rule by, the rule is the Fleming's left-hand rule. Okay, so in the Fleming's left-hand rule, the thumb indicates the direction of the force. Index finger represents the direction of the field, and the middle finger represents the directions of the positive charge. So in which direction the positive charge is moving, that's the direction that you'll have to point your middle finger to. Now, in this case, if we assume that the positive charge here is moving in that direction here, I will try to make a Fleming left-hand rule so that it fits the situation there. So you can see that our index finger, the direction of the field is sideways. So it goes from north to south. So it's sideways, north to south. I have to point it like that. And the direction of the positive charge is inside the page. So I make it like this. It's inside the page, right? It goes inside. So you see the thumb is pointing downwards, right? So if the thumb is pointing downward, then the force acting on the charge is also downward like that. So this is the directions of the force acting on the charge for this particular situation. Now let's look at a different scenario where the charge is moving out of the, it's coming towards us like this. So if it's coming towards us, then again, the direction of the field is not changing, so it's the same. But now they force the current, the charge is moving towards us, so we have, the middle finger has to point us. And you see the thumb, it's pointing upward, right? So that's why the force is upward. So it's basically saying that if the charge is moving towards us through the magnetic field, you will see that the charge is moving upward. Okay, so that's because the direction of the force was upward. So with that, we're done with the forces on a charge moving in a magnetic field. We'll conclude by doing some simple questions, and after that, we're done for today. Okay, so let us do one simple question here. So if we have a charge of 20 microcoulomb moving at 100 meters per second in the field as shown below, we have to find the magnitude in the direction of the, excuse me, this should be a force. Magnitude in direction of the force here. Okay, so we have the formula here. So force equals to BQ V sine theta. The magnitude of B is 0.1 Tesla here, times the magnitude of charge is 20 into 10 to the minus 6, because it's a microcoulomb, times the velocity is 100, times sine of 90, right? Because in this case, you see that the field is in that direction here, and the charge that's moving is perpendicular to the field. So it should be 90 degree here. So sine 90 is 1. So if you type this in the calculator here, you will get around 2 into 10 to the minus 4 Newton. 2 into 10 to the minus 4 Newton. Now, in which direction is the force acting on? So again, using the Fleming's left-hand rule, the field is from left to right, right? So field is from left to right. So I point my index finger, and my charge is moving inside the page here. So it's going inside the page. So the middle finger has to point inside the page, and you see the thumb is down. So the force is acting in the downward direction. Okay, so therefore you can just say that the force of 2 into 10 to the minus 4 Newton acts downwards. So that's it. So we'll do that much for today. I'll see you all in the next class. Take care. Bye-bye.